Hey gang, welcome back to Chem 127. This is lesson number 10, continuing our discussion of the Earth's radiation balance. And today we kind of turn the corner and do a cosmic pirouette with the radiation, if you will. We've kind of been following it in through the atmosphere and talking about what happens physically and chemically as that radiation passes through the atmosphere to the surface. Now we're going to stop and talk about what happens as it goes out. One of the things we'll do, however, is disregard the atmosphere altogether and actually do a simple model where we can predict the temperature pretty well in the absence of an atmosphere. That's accurate for a planet like Mars with very little atmosphere, but not so good for us. But as a platform for introducing this idea of something called greenhouse warming, we'll do a little thought experiment on how that works and finish up with some accounting where I hope you can grasp the magnitude of the greenhouse effect. This was a pretty important realization for me when I realized whether the greenhouse effect was a big deal or a little deal. We're going to be reading the first half of the ECS reading, and this stuff is in homework number 6. Another little weird thing about this video is that as soon as I hit stop here, you're going to be teleported into my living room where this was shot. Most of this was shot a couple years ago, so we'll see you there in just a second. Okay, again, we're in the process of looking at this radiation balance. We followed the radiation going in. We talked about things that it can bounce off of and reflect, and even how human activity can affect those things. We talked about the chemistry that occurs when this UV is absorbed in the ozone layer. And now we're going to look at the outgoing radiation. And as we'll see, the sort of big part of this story is that the role of the atmosphere has these things in it called greenhouse gases. And the way that human activity can affect average global temperature is by changing the chemical composition of the atmosphere in a way such that it enhances or mutes this thing called the greenhouse effect. And today we're going to focus mainly on the general properties of that thing. Okay. I gave you a sheet a while ago, and I invited you to hand it out, to print it out and go along with the lesson again today. I don't have my copy here, but I do have a couple other handouts that I want to get handy. Just the idea of framing this in terms of questions just kind of makes you a little more hungry for the information. If you know what questions we're trying to answer, the answers are bound to make more sense, right? So now as we turn to the outgoing radiation, we want to look and see, what wavelengths are emitted by the Earth. Do they differ from incoming wavelengths, and why? And I think you probably figured the answer to that is, yeah, they're going to differ because the Earth is cold and the sun is hot, and the Earth is going to emit infrared, which escape, which absorb. As we'll see here in a bit, not all of that outgoing radiation goes through the atmosphere. In fact, most doesn't. There's only a small little piece which goes straight through the atmosphere, and that's got important ramifications for how certain greenhouse gases function. And then it's a question of what absorbs them, where are they, what happens to these molecules when they absorb them, how can we predict the ones that will absorb, and which will have the greatest impact ultimately there at the end, and if human activities affected their abundance. In other words, if we're going to put stuff in the atmosphere that's going to affect the radiation balance, ultimately we want to know which stuff has the largest impact, and then also the quantities of stuff that we have put out there. So going forth here, let's revisit this picture of the radiation balance. All right, the idea here is that this incident solar radiation needs to be balanced by the radiation going back out, either the sum total of that reflected plus that re-emitted, or the other way that we could look at it is that the sum total, which is incident that doesn't bounce off, is equal to that is re-radiated. And we're going to look at this quantitatively today to sort of see what kind of quantities are involved in this radiation balance. Here it is in pictures. Now, some time ago, we went through and talked about what kinds of radiation is given off by macroscopic bodies and how we can predict that. And what that was all about was these things called black body radiation curves. And the one thing that I told you about the black body radiation curve, be it a real sharp one like this or be it a real broad one like this, is that the total energy incident or emitted by that system, the total energy emitted by that system, this one happens to be incident, is equal to that total area. Okay, so we ought to be able to show the radiation balance of the Earth in a couple of pictures. Now, this broad thing here is the black body radiation curve for the Earth. And notice it's got lambda max here far out in the infrared at about 10,000 nanometers or 10 microns. And that, if that area is the total energy, then that's got to be equal to the total area of the incident radiation that is absorbed. So this sharp black body curve here is a black body curve for the sun, but it's not for the entire sun because that would be much huger than the black body curve for the Earth. But rather, it's the black body curve. Excuse me there, I just had to sneeze really bad. This is the black body radiation curve of sunlight, of the sun, but only the part that's not only incident on the Earth, but also absorbed by the Earth. So if we said this is the radiation that gets absorbed by the Earth system, and that area, the total energy in that side of the radiation balance has got to equal this area, the total energy on the re-emitted by the Earth side of the radiation balance. So that's a way we can show this in pictures, and I'll revisit these pictures to sort of show you a mechanism for how a greenhouse gas works that's just sort of a thought experiment. Okay. What we're going to do now is shift to a little exercise in climate modeling, just to sort of get quantitative here and show that that we can predict the temperature of the Earth, and for that matter Venus and Mars, in the absence of an atmosphere with some relatively simple algebra that I'm still not going to grind through, but I think I can convince you of the rationale. So the idea is I've just taken some of the garbage out of the pictures here, and here we've got our incident solar radiation. Again, that's incident on the Earth. Some of it's going to bounce off, some of it's going to be swallowed up by the Earth and re-emitted, and those are the red arrows here. And if we're going to compare Venus and Mars, well, let's put them in the picture here. Mars is out here beyond Earth, obviously not always in the shadow of Earth, but in this picture it will be. It's a little further away. And one of the things is that these rays from the sun are divergent. So as they diverge, there's going to be a lesser concentration of those hitting Mars. If you will, the sun is going to be a little less bright because you're further away. And this divergence of the rays and how many rays there are hitting per unit area is a quantity I'll define in a second called the flux. Okay. Vice versa, Venus is closer. It's closer to the Earth. Those rays haven't had as much time to diverge, so there should be more solar energy hitting Venus per unit area. And again, that's a quantity we call flux, which is very important in the radiation economy. And one of the reasons that I really didn't care for second semester physics very much as I thought I might be a physics major in college. That's kind of a tricky concept. I think I can gloss over it and convince you guys as to what it is. Okay, so let's try to quantify the radiation balance here. Now what I'm going to do here is saying I need to quantify this incident absorbed solar radiation, so the yellow stuff that doesn't bounce off, with the sum total of these red things, for that matter for all three planets, but I'm just going to do it for Earth first and we'll plug the numbers in. Okay. Let's start this with a true or false question. Just sort of sold you the idea that the energy density incident on Venus was higher. So I'm going to ask you a true or false question. I'm not going to answer it yet, and that is, it actually shouldn't be a question. It's a true or false statement. Venus is hotter than Earth because it's closer to the sun. Seems like a reasonable thing too. So let's think about that as we go forth here. Okay, so what we need to do here, and by the way, I have a sketch of this on this little handout that I posted for you today. We need to say that the area in this sharp curve is equal to the area in this broad curve, and let's grab some concepts here to kind of piece this part of the puzzle together. Okay, so again, the Moral of this quick little story here is that with no atmosphere, climate modeling is actually relatively easy. We just got to set the incoming radiation equal to the outgoing radiation, and we can borrow some concepts from physics to see what that is. And again, I'm not going to make you do this derivation. I'm really just trying to show you that there is some logic to this, and say relative to running a global climate model on a supercomputer, that this is a pretty logical thing, and we can learn some things from it as well. Now, the key currency when we talk about the radiation balance is this idea of flux. Flux really is a way of getting the density or the concentration of the rays of solar radiation or other radiation incident per given area. So the idea is that for a given area, how much energy is flowing through that area per unit time. So it kind of has to do in part with how concentrated the rays of sun or the rays of terrestrial radiation are. Right? And if we multiply that flux times the area, we get energy per unit time. And that's what in both of our instances here in terms of looking at the planet, we're going to multiply these things that we can borrow for the flux times their pertinent area, and that'll give us power, which is energy per unit time. Power has units of watts, like a 100-watt light bulb, for example, which is just a joule per second. It has to do with how much energy it uses per unit time. You can just think of power and energy as the same, and we've got a certain amount of energy flowing through this region, and then the total energy has to do with taking that energy per area and multiplying it by the area. So incoming radiation has to do with the concentration of the incident solar radiation, which is that 1380 watts per meter squared, that the solar constant. That's a quantity that's unique to the Earth for how concentrated the sunlight is when it reaches the Earth's surface. We've got a correction factor here that is 1 minus the albedo. In other words, only concentrate on the part that's absorbed by the Earth system and factor out the part that bounces off. And then this is energy per unit area, and then we just, if we're looking at the Earth from the sun, we see a disk, and we're going to multiply that by the area of the Earth. That's the incoming absorbed radiation. Okay. The outgoing radiation, really all we can do is borrow this formula from physics, which is this constant S times temperature to the 4th power. S has this value here, roughly 5.7 times 10 to the minus 8 watts per meter squared, Kelvin to the 4th, kind of screwy. But this is just a formula that says for how hot a given object is, how much radiation will be coming out of it per unit area. In other words, what is the flux of radiation out of an object per unit temperature? And then if we have flux and we multiply by the total surface area of the Earth in this case, because the Earth would be radiating from all surface, the surface area of a sphere is 4 pi r squared. Set these things equal, call this temperature the effective radiation temperature, which is what astronomers call the temperature of a celestial body obtained this way with no atmosphere and no greenhouse effect, and voila, here's your effective temperature. Okay, let me just explain this formula now and what the numbers in this mean. Okay, this is this thing called the effective radiation temperature. Again, this is the temperature of a celestial body located some distance, presumably from a star, such that it has some kind of incident radiation on it in terms of flux, which is this Fs constant. Okay. Based on the properties of that particular celestial body, some of that radiation is going to be reflected, and we carry that quantity in this thing called the albedo, and the amount that's absorbed is therefore 1 minus the albedo. This 4s quantity, s is just this physical constant, 4 was just a part of the derivation, and at 1/4 power is part of the derivation. So essentially, if we look at what this says, is that, well, if Fs, which is the amount of incident radiation, goes up, the temperature is going to go up, right? Because if that number gets bigger, that number is going to get bigger. As the albedo goes up, right, more radiation is reflected, but then 1 minus the albedo will be a smaller number, and that will make this go down. So there is some logic to this, and that is that there's more incident radiation on the planet would tend to drive it up. That would enter into this equation in that Fs number. A larger albedo, higher reflectivity would make the temperature go down, and that enters in this here. It doesn't. The part it doesn't have is the greenhouse effect. That's how this formula works. Now what I'm going to do is plug some numbers into this thing to get the effective radiation temperatures of Earth, Mars, and Venus. and then we'll talk about them next. I'll just do my calculator work and sort of grind through some of the numbers here so that you can see how to do this. We're really interested in the end result here, so don't worry about this if this formula is just a little bit obnoxious.